Good afternoon, everyone. Myself, Chitransh, along with Vibhor and Jnana, will be presenting a paper presentation on the topic SinGAN, learning a generative model from a single natural image. Next slide. So the content of the presentation is introduction, related work and comparison with other methodology, model architecture, loss analysis, result, quantitative evaluation, application of SinGAN, conclusion and references. Next slide. In the introduction, we propose SinGAN, a new unconditional generative model trained on a single natural image. Our model learns the image patch statistics across multiple scales using a dedicated multi-scale adversarial training scheme. It can be then used to generate the realistic image samples that preserves the original patch distribution while creating the new object configuration and structure. In this, our model is getting trained to capture the internal distribution of the patches within the scheme and is then able to generate the high quality, diverse sample that carries the same visual content as that of the image. Specifically, we show the internal statistics of the patches within the single natural images that typically carry the enough information for learning a powerful generative model. Here, this can be achieved by a pyramid of fully convoluted, lightweight GANs where each is responsible for capturing the distribution of patches at the different scale. So here we can see that in the training we have given a single image and we can see that the random sample of the single image has been generated. The first image is the mountain image and the second one is the bird image. We can see that the generated image has the same visual context as that of the single image. Next slide. Now, since once the SinGANs is trained, it can produce a diverse high quality image sample of arbitrary dimension which semantically resembles the training image and yet contains the new object configuration and structure. Modeling the internal distribution of patches within the single natural image has been a long recognized as the powerful prior in many computer vision tasks. Classical examples include denoising, deblurring, super resolution, dehazing. Here, we can show the many image manipulation task has been performed by the SinGAN. In all the case, the model produces the high quality results that preserves the internal patch statistics of the training image. We can see image to paint, editing, harmonization, super resolution, and animation. We have given training image, input image, and finally we can see the output of all the processes. Next slide. Here we will compare our method with the related methodology. We have single image deep networks which mostly faces the problem of overfitting when we are getting trained over a single images. These methodology basically requires a large amount of data sets to get it trained and to produce the variety of the images. However, we are losing the texture of the natural images as that of the given trained images. But here in the SinGAN, all the work can be effectively done on the complex texture and the non-repetitive structure, and hence it can be used to generate the natural image. We can see that where we have given the training image, it can be produced by PSGen, deep texture synthesis, and SinGANs. Next slide. Now, coming to the model architecture, our goal is to learn an unconditional generative model that captures the internal statistics of the training image X. This task is conceptually similar to the convolution GAN setting, except that here the training samples are the patches of single image rather than the whole images from the dataset. Now, to achieve this model, our generative framework, which is illustrated in the next slide, consists of the hierarchy of patch GANs where each is responsible for capturing the patch distribution at a different scale of X. Our model basically consists of the pyramid of generator varying from G0 to Gn trained against an image parameter of X which is varying from X0 to Xn, which is basically downsampled by the previous version of X by a factor of r to the power n. Here, each generator Gn is responsible for producing the realistic image sample with respect to the patch distribution of the corresponding image x of n. Now, this can be achieved through the adversarial training, where G of n learns to fool an associated discriminator D of n, which attempts to distinguish the patch in the generated sample from patches in Xn. Next slide, please. This will show the overall architecture and the overall process of the SinGAN in the multi-scale pipeline. So here we can see that our model consists of the pyramid of GANs, which is basically in the pink color, where both the training and the inference are done in the coarse to fine fashion. Means we are moving from the coarser level to the finer level to analyze the patches of the image. Here at each scale, GN learns to generate the image sample in which all the overlapping patches cannot be distinguished from the patches in the downsampled training image x of n by a discriminator dn. Now, the effective patch size is decreases as we go up in the pyramid, which we can see in the right side. We can see the image patches are getting reduced. It means that the analysis is going to be done from the coarser to the final level. Now, the input to the g of n, the input to the g of n, next back, can you please back? Now, the input to the G of n, the input to the G of n is the random noise image Z of n and the generated image from the previous scale xn, which is upsampled to the current resolution. Here, the generation process at the level n involves all the generators given from the G of n to small g of n and all the noise, generator, noise, and images. And finally, at the training progression, we are reducing the patch size to go ahead the final level. Next slide. Now, this is one of the part of the overall architecture where I will be explaining about the single scale generation. So here we can see at each stage of n, the image from the previous scale xn plus 1 is upsampled and added to the input noise map Zn. Now, the result is fed into the 5 convolution layer, which is shown in this figure, summed up, and whose output is the residual image, which is again added back to the xn plus 1. And this can be treated as the output xn of the generator gn. Now, coming to the losses, Jana will explain. Thank you.
Thank you, Sagar. I'll go next. So, as we see from previous architecture, the our model trend from the bigger size patch to the smaller size patches. So, while training, we come across two type of losses, and those are adversarial loss and reconstruction loss. So, once we are training this pyramid of GANs, the GANs are kept fixed, and the training loss we can say is like minimum of generator and maximum of discriminator loss, and L adversarial loss plus alpha L reconstruction loss. Will while adversarial loss is the difference between the patches generated and the original sample patches. So the model actually penalizes the model through this, and the reconstruction loss is ensures the existence of specific set of noise maps that produces XN. We'll go in detail in the next slide. In adversarial loss, the generator with Markovian discriminator uh, classifies each overlapping patch whether it is a real one or a fake one. So in this case, we use WJAN GP loss, which actually increases training stability. So the final discriminator score is nothing but the average of patch discriminator map, as opposed to single image GAN for textures, where we compare the loss of the whole images, then random crops. So this is an important feature of our setting, and the architecture of DN is same as Psi. within the generator. In terms of reconstruction loss, we want to ensure that a specific set of input noise maps which generates the original image. We choose reconstruction from Z reconstruction N to Z reconstruction 0 with a fixed noise map, so which can be defined by the highlighted equation Gn0 x reconstruction loss plus n plus 1 minus xn square. So reconstruction image has a another role in terms of training. It used to determine the standard deviation of the noise at each scale level. So sigma n, which is proportional to root mean square error between Z reconstruction n plus 1 and xn. The more indicator we can see in the next slide. So as we can see here, it's a low resolution image. We are trying to get a super resolution image of through part of it, and we can see through SinGAN, our output is very much comparable to the best quality models available, and it outperforms other models. Next things Vibhor will take. Thanks.
Thank you, Saga. Thank you, Gyana. So, hello everyone. So, I'll be presenting the results of SinGAN. So, as a whole, if we'll see the result of this model, it has made a good, remarkable progress on qualitative and quantitative variety of images. If we span large range of scenes, whether it is urban or nature, in this paper, the author has shown that they have generated random sample with same aspect ratio and the original image, but with decreased expanded dimension. And we can see that SinGAN architecture is resolution agnostic, and it can be used on high resolution images. And one more thing that resulted in this model is that it preserves the global structure of the objects like mountains, air balloons, or pyramids. Next slide, please. So now you can see here, so the training, after training the images at the leftmost corner, that our model has generated a realistic random images sample that has obtained a new structure and object configurations, and yet it has preserved the patch distribution of the training images. This is because our model is fully convolutional and the generated images can have arbitrary sizes and aspect ratios. Next slide, please. So now here we will see a quantitative evaluation. So in quantitative evaluation, we have used two statistics. One is Amazon Mechanical Turk, and another is a new single image version of Inception Deception. So now you can see in the first two images, the tree one that you are seeing and a square, whole square one, it has obtained a very minute adversarial network which has created a new scenes. And on the right hand side, now you can see the training images on the left hand side. When we have taken two scale or four scales, the image qualities that obtained were not of too much of information, but when we have increased the scales, it has depicted a good amount of scales features. Next slide, please. So now you can see that how much diversity survey and confusion means confusion metric result it has resulted in the first scale n and n minus 1. And another one on the data means metrics is SIFT, that it has related means produced a very good results that we can see from this table. Next slide, please. So now in this slide, I'll be describing about the application of SinGAN, where it will be applicable. So SinGAN is applicable to the paint to image transfer clip art from to a photorealistic image. How we can achieve it is by downsampling the clip art image. Another thing, another application of SinGAN is harmonization. Realistic means blend a pasted object with a background image. And another application of SinGAN that you can obtain a video from an input image. Next slide, please. So another that we have just discussed, that application harmonization. Now you can see that SinGAN has generated another set of feature from the input image, and that is of more high resolution and depicting features in a good amount of resolution and quality using harmonization. Next slide, please. So, with this being said, we wanted to conclude about the SinGAN presented in this presentation. We can see that it is a generative scheme. It is learned from the natural image and demonstrated its ability to go beyond texture and generated diverse realistic sample for natural complex images. And with this being said, now the training image containing a single dog is not trained on this model, so it will not result into the sing means a different dog breeds. So we can say with this that SinGAN can provide a very powerful ability for a very wide range of image manipulation tasks. That's all from our end, and this is the references. Any questions, you can reach out us via our email address. Thank you.